I've got some 2 molar hydrochloric acid and some metallic zinc. And we're going to mix these together, see what happens. So we'll pour some of our 2 molar HCl into the flask. That should be plenty. And then we'll take some zinc, and we can notice that it's just chunks of metal. And what I'm going to do is take some of these chunks of metal and just toss them into the flask. Maybe 3 or 4. And it may look a little bit cloudy, and that is actually because we're starting to form some bubbles. Let's really zoom in on this and see if we can see it more closely. We can definitely see bubbles of gas forming from the surface of the zinc. And the question is, what is the identity of that gas? Now this is aqueous hydrochloric acid, so it could be chlorine gas. Now, chlorine gas has a characteristic smell, and I know you can't smell this on the video, but I can't smell chlorine either, so it's not chlorine. It could be hydrogen, either from the HCl or from the water, or it could be oxygen from the water. Now, if we were to collect this gas and perhaps fill a balloon with this gas and light it, we would see that it would burn, much like the hydrogen balloon that we saw in a demonstration back when we were talking about thermodynamics. So in fact, we're forming hydrogen gas, and we're also forming zinc 2+ ions. Now, they're colorless, so we're not going to see them. But if we let this sit here long enough, the zinc metal would go away, and all we would have is a clear solution. What we saw was an electron transfer, or redox process, which is represented by this balanced equation. 2 hydrogen ions and solid zinc go to form dihydrogen gas and zinc 2+ ions. We see that the oxidation state of hydrogen goes from +1 to 0, indicating a gain of electrons. So in the reduction process, hydrogen ion is reduced to dihydrogen. We also see that the oxidation state on zinc goes from 0 to 2+, indicating a loss of electrons. So in the oxidation process, zinc is oxidized to zinc 2+ ions. Now, we could have used a number of metals, iron, lead, tin, and so forth, and the hydrogen process would have been the same. So you often see the reduction and oxidation processes written as separate balanced equations called half reactions. In this case, the reduction half reaction has 2 hydrogen ions gaining 2 electrons to form dihydrogen. The oxidation half reaction has zinc losing 2 electrons, going to zinc 2+ ions. Notice that when zinc loses 2 electrons, they appear on the product side of the half reaction. The other thing to point out here is that half reactions are always balanced, both in terms of number of atoms and in charge. It just so happens that in our 2 half reactions, the total charges are 0 on the reactant and product side. You'll see some later on when they don't add to 0, but they are still the same on both sides. When you add the 2 half reactions together, the electrons will cancel out, since they are a reactant in the reduction and a product in the oxidation, and you get the whole reaction. We should note that there will always be a reduction and an oxidation in an electron transfer process, because somebody gains and somebody loses electrons. And since we have a reduction and an oxidation, these reactions are usually called redox reactions. One further piece of language regarding these half reactions. The reactant and product in a half reaction are often referred to as a redox couple. For example, in the reduction process, we have the hydrogen ion dihydrogen redox couple. In the oxidation process, we have the zinc 2+ zinc redox couple. In both of our listings, the species with the more positive oxidation state is listed first, regardless of which one is the reactant and which one is the product in the balanced half reaction.